So let's take a close look at this histogram. It's the histogram that represents the egg diameter of rainbow trout. It looks like the average or the mean is about here, and it indicates here as well that the average is 4.31. It tells you, for example, that there are just over 4, looks like about 5 eggs that are between 3.9 and 4 millimeters wide. So the histogram is a description of measurements that were taken in the field. But what I want you to take a look at here is that it has the shape of a bell curve. It is not perfect because this is not completely symmetrical with this, but it's pretty close. And so we would call this a normal distribution. So the characteristics of a normal distribution is that it is bell-shaped. There are no outliers. And bell shapes implies that it's symmetric or roughly symmetric. And we are going to be talking a lot about the normal distribution in the rest of this unit. So from the last slide, we knew that the rainbow trout has a normal distribution because of the shape of the histogram. We're going to approximate that histogram or turn it into a smooth curve instead of a graph with a whole bunch of bars in it. So notice that it's now become a smooth curve with the shape of a bell, and this is called the normal distribution curve. And the peak of this curve has to happen at the mean, just like the histogram had. So the mean was 4.31 millimeters, and it happens at the peak. That means that most of the fish, as this is going to represent the probability of something happening, most of the fish are going to have a egg diameter of 4.31 millimeters. So the other thing that we were told in that histogram is the standard deviation is 0.25 millimeters. They didn't show us how that was calculated, but we're going to learn how to do that in future lessons. Right now, I want to just make sure that we know how to add that information to the distribution curve appropriately. So what you want to do is you want to use your bell curve and you want to evenly space everything to the right here into 3 equal segments. So I'm just going to eyeball it a little bit here. So that's about 3 equal segments. And then the same thing on the other side. And then each of these segments goes up or down by 0.25. So if I add 0.25 to 4.31, I get 4.56. And then if I add another 0.25, I get 4.81. And lastly, if I do it one more time, I get 5.06. Now, if I'm going in the other direction, I'm going to subtract 0.25. So that would be 4.06, 3.81, and 3.56. So we're remeasuring you're using our standard deviation to set up a scale. So this in effect is 1 standard deviation away. This is 2 standard deviations away, and this is 3 standard deviations away from the mean. This is down 1 standard deviation, down 2 standard deviations, and down 3 standard deviations. So what this bell curve is saying is that there are very, very few fish that have a egg diameter of 5.06 millimeters. Or on the other hand, very few that have a diameter of 3.56. Most of them are in the middle. And the area underneath this curve represents the probability of egg diameters. So if we take a look at the area underneath this, all of this represents 100% of the eggs. So there are going to be nearly 100% of the eggs have a egg diameter between 3.56 and 5.06. There's going to be very, very, very few of them that go beyond 5.06. And we'll be doing some calculations with this in the upcoming slides. So let's take a look at the same distribution. This is still about rainbow trout. And so we're talking about egg diameter in millimeters. And this should have been in millimeters here, sorry. So we have what percentage of trout eggs are between 3.56, so here's 3.56, and 5.06. So that means nearly the entire curve. There's only just a little bit missing, this little bit on this side and this side. So it's nearly 100%, and it's nearly, I'm just going to put nearly 100%. And more accurately, it's actually closer to 9.7%. And we're going to have a table that we can look those things up on. So the second question is, what percentage of trout eggs are larger than 4.31 millimeters? So 4.31 millimeters is the middle. And which ones are larger? So that's half of the bell curve. So that is 50% of the eggs. So I want you to focus in on the right side here, this right graph, and this is called a standard normal distribution, and it's based on calculations mathematicians have made that approximate the different areas depending on how many standard deviations they are from the mean. So if I use the mean in the middle, and I go one standard deviation on each side, that represents 68%. Now it's going to be helpful to actually split that in half, and half of 68 is 34. So this side is 34%, and so is this one. If I go two standard deviations, it's 95%. And if I want to calculate what this little bit is here, so it's 95 minus 68, which is 27%. And because I'm splitting that into two, I get 13.5%. So each of these little pieces here is 13.5%. And if I do that again for going three standard deviations, it's 99.7. And if I cut that, if I subtract the 95 and split it in two, I'll get each of these is 2.35%. So this curve that I have on the right in its original form, it'll be given to you as a reference on any assignment or any test, and you can use that to approximate applied problems that have a standard deviation that's different, like the one for the trout eggs, for example. So if we go back to the trout eggs, and this is again supposed to be in millimeters, sorry, I've still got the same label, and this is going up one standard deviation, two standard deviations, three standard deviations, and down one, down two, down three. So now I'm going to use that information to answer the question about what is the probability of a trout egg having a diameter larger than 3.56. So 3.56 is right here, and it's going to be larger. So if I compare that normal distribution to my standard normal, this is called the standard normal, I can see I can add up the percentages. It's this piece plus this piece. So it's 13.5% plus 2.35%, which equals 15.85%. And if I rounded that up to the nearest percentage, it would be about 16%. So 16% of the trout eggs have a larger diameter than 3.56 millimeters. So let's do that again. Again, this should be millimeters and millimeters. And this time I'm going to use 3.81. Here is my lower bound. So that's at 2 standard deviations down from the mean, to 4.81, which is 2 standard deviations above. And I want what percentage does that represent? Well, if I compare that to the standard normal, it's 95%. So one more time, we're going to be taking a look at what the probability is of trout eggs being between 3.81 millimeters, I made this mistake all the way through, and 5.06 millimeters. So on our curve where we have labeled the x values, or the diameter of the trout eggs along the horizontal axis, 3.81 occurs here, and 5.06 occurs here, and we're looking for the probability, which is represented by this area. Now I'm going to use the standard normal to do this. We've gone 2 standard deviations down from the mean, so that represents this, and we have gone 3 standard deviations up from the mean, which is all the way to here. So this area is what we're looking for. Now notice that between here and here is 95%. And then I have to just add this little tail end, which we did in a previous problem. We figured that was 2.35%. So that gives you 97.35% probability that the eggs are going to be between the given range.